All right, get this started. Hello and welcome to the 8th Long Products webinar. I'm Kevin Landau, staff engineer at AIST. This webinar is titled Improving Periodic Defect Detection in Hot Rolled Long Products by Means of a Combination between Eddy Current and Vision. As with all our AIST events, we have antitrust guidelines. So if do not discuss with others your or your competitors' pricing procedures, or anything that might affect pricing, such as costs, discounts, terms of sale, profit margins, or anticipated wage rates. Do not make statements about your own pricing or of those of your competitors. Do not talk about what individual companies plan to do in particular markets or with particular customers. AIST also has anti-harassment policy, which is listed there. And the things to know. The attendee audio has been disabled. We are asking that all questions go through the Q&A feature that's on the bottom of your screen. So if you hover your mouse towards the bottom of your screen, you'll see the Q&A that will open up. That will allow the presenter and the moderator to see the questions, and the question and answer will be after the presentation.
First of all, I'd like to welcome everybody to this webinar this morning. So our speaker is going to be Jose Ignacio Lucas. He's the Director of Sales and Marketing at ISEND, a company focused in industrial non-destructive testing solutions for surface quality control. He's a member of the management committee of the company, and he's also been actively involved in the development of new solutions, as well as in some R&D projects. He holds a degree in physics from the University of Salamanca, and he's Chief Executive certified by the INSEAD Business School in Fontainebleau, France. He joined ISEND almost 8 years ago with a mission to develop the company's portfolio of customers and projects. Previously, he spent most of his professional career at IBM as a solutions manager in the industrial and aerospace defense sectors. He's a specialist in non-destructive testing solutions for long products and digitalization of large companies, in enterprise resource planning and customer relationship management systems, and in the application of artificial intelligence to business practices. So with that, I'd like to turn the presentation over to Jose.
Okay, I'm sharing my presentation right now. I hope everything is okay in your screen.
Looks good.
Okay, so I'm ready to start when you want.
Jose, it's all yours.
Yep.
Okay. First of all, thank you very much to everybody attending this webinar. Probably it is a very, very nice morning in the US. It's a wonderful evening in Europe, in Spain, where we are the honor and proud to talk from here to show you this webinar. I hope it's interesting for you. And this webinar is based in a paper that we presented 2 years ago in the ISTEC Philadelphia. And was developed with one of my best colleagues, that is a big expert in rolling mill process, that is Bruno Sedal. But we have tried to approach this webinar from the next step point of view. So we are going to present this webinar that which title is Improving Period Defect Detection. And we are introducing a new paradigm, a new idea, a new technology to detect periodic defect detection in rolling mill operations. That it can be applied to any kind of defect. Also, it can be applied also in coil production. Also can be applied to flat products, not only long products. But we have focused our presentation in the long product detection because periodic defect detection in hot rolling mill operations is something that is very difficult and is very critical for many operations. And it is a good example will focus our idea about the evolution of the technology trends in a short term, and we don't know if in a medium term, but probably medium term for us is far away from our point. So in a short time, this webinar will be divided into 5 sections. The first one is an introduction to the market, and in this introduction, we will try to focus with this our main motivation and how we have developed our solutions in this way, including the second phase is make a very brief overview about Eddy current technology, digital imaging, and the state of the art of both technologies. And in the third one, we will try to introduce the concept of integration of different technologies. So with all these elements, we will try to put light in the period defect detection problem. And finally, we will try to make a brief summary just to reinforce the main ideas we will try to transmit. I will try to be, or I will try to get your question and answers from the Zoom section of the screen, but I'm not following the question and answer in real time. So excuse me if I defer to the end of the presentation, this question and answers. And anyway, we can send all the questions you have enough for the time, just in offline mode, and I commit to answer to every question you can put. The first one is to take a look at the market trends in 2021. This is a very special year, of course. This is not a standard year. It has been something strange due to the COVID, due to this disease situation. But the question is that even these trends are based on a special or very special COVID situation. We consider that in the future, many trends will be due to specific moments in time. So 2 months ago, we performed an internal research with our customers, and we get some findings. Some of them are in this presentation. 73 of the companies believe that the steel prices will grow in 2021. And this is something that is happening. You can see on the right, this graphic with the evolution of the steel prices. Second is only 20% consider that quality is one of the key success factors to improve gross profit. That's something that is, for us, is very strange, because quality is a way to get better prices. So it's a good way to go to profitability of the company. So 20% we consider that is not so high value. Then 60% consider that automation, the digitalization and industry 4.0 are the priorities to reduce costs. Obviously, it means that the 45% more or less are considering to increase hiring related to the previous knowledge areas. So this is more or less something that has left the current situation, the market trends. In parallel, we have a set of technology trends. Technology trends that probably most of you have listened in any situations or apply to general business. And we are going to apply some of these concepts to the iron and steel industry. The first one is the Industry 4.0. What that means, Industry 4.0, is the interconnection or the connection between different elements, sensors or actuators in the production line in real time, and even inside and outside the company with vertical integrations of some operations and so on. Second one is the Internet of Things or Internet of Things and 5G connections that will allow this real-time connection between sensors and actuators in real time, and in a wide band of connection without the restrictions of the current 4G networks. Third one is big data management. We don't know any company that is not concerned about how can they use big data to analyze the information that is coming from inside, but also from outside the company. And big data, it goes much further than the question of taking information from internal systems, because big data means to combine structured data that probably is coming from your own information in the company with unstructured data coming from the outside, coming from the internet, coming from different reports and so on. The next trend and big trend is the artificial intelligence. It's how to use algorithms, how to use different algorithms to manage in real time big data. All these elements are connected. It doesn't mean that you need to go to all the elements at the same time, but for artificial intelligence, big data is required to build good algorithms, but also you can build algorithms only with less data. So there is a relation, a correlation between all these elements, but it's not exclusive. Automation is other element that is directly related with robotics, is the automation of some tasks that until now has been performed by humans, but with the artificial intelligence algorithms, and all these elements are becoming something that is that some systems, and a production, a rolling mill is a system, are starting to take decisions without the human's participation. Obviously, and in my opinion, artificial intelligence makes sense only in combination with some human aspects. And the artificial intelligence is something that can help you to reduce the volume or the size of certain tasks. But the artificial intelligence, at least until now, has a lack in one of the most important sense, that is let's say, I mean, the common sense. Artificial intelligence has a very rational mind, but has not a very emotional mind and an intuitive mind. So artificial intelligence is good, but it's not enough. And I think in the future, it won't be enough. So it's a good perspective for the people that is willing to use artificial intelligence like a tool, because the combination with the human experience is absolutely critical. Other element is the virtual and augmented reality, is the possibility to mix real images with artificial projections. For example, imagine you have to fix a broken roll in your rolling mill, and you could use glasses or a screen where you can see the whole rolling mill. It can guide you to the broken roll. It can guide the way to remove this broken roll and to replace for another one. All these elements are very important because you don't need to train your people before. You can use augmented reality or virtual reality to facilitate some maintenance tasks or some changes in the line. Of course, cloud computing. Yeah, and I know that is a very sensitive area, especially in the iron and steel industry, that is not is not willing to share the information in the cloud. But this is something that is necessary, because the cloud has some question that you can feel uncomfortable with security reasons or issues or whatever. But the real situation of the cloud computing is that it's safer than the own information system, because in the cloud you can establish 100,000 of security checks to avoid hacking or other kind of information. So I really think in the cloud as a way to improve the digitalization of the companies. Of course, the edge computing. What is edge computing is exactly something that we have all in our mind, that is some sensors, some current sensors in the real life are able to make small information processing before to send information to the central information systems. For example, if you are taking information, for example, with your mobile phone, before sending this information to your system, some processing can be done in the mobile phone. So the edge computing is to distribute the information processes between small devices and the central systems or even the iCloud and so on. And finally, the blockchain, that is a new way to use to take or to control the tracking of different elements of different products and different components in the line. In the right side, there is a picture with the main building blocks of the intelligence or the artificial intelligence that are relevant for the iron and steel industry. The first one is pattern recognition, that we will talk about this in our presentation in a couple of minutes. That is the potential to recognize images directly from the source. Also the automation, artificial intelligence in terms of different learning algorithms or learning approaches like machine learning, like neural networks, data mining, algorithms, and finally to problem solving. In our presentation, we will give you an example about how we use artificial intelligence that include machine learning, that includes neural networks, and that include pattern recognitions in the area of periodic defects in hot rolling mill operations. And finally, for this introduction, there are some social trends that are changing the way we consider the iron and steel industry. The first one is a wave that is to reduce emissions. That now is the big challenge for every company, to reduce emissions by using but for example, using hydrogen or using another ways to melt the metals. The ethics and values, including in these ethics and values, some elements that are changing our conception of the company. Now it's very important in terms of the companies to retain the talent of the good people, and it means to make a big effort to match the ethics of the company with the ethics of the people. And this is something that is changing also our perception of the world. The green economy is very related with reduced emissions, obviously, but the green economy is trying to go further, and the green economy means all the standards or all the laws that are coming from the governments, and that is changing the way that some products are introduced. The electricity in travel and transportation, starting in vehicles, but also in the other elements, that the industry of the automotive industry is changing a lot in the last 1 or 2 years, going to electric vehicles. Probably we'll see something similar with aerospace and defense and so on. And finally, we are facing a workforce transformation. So the way we understand the workforce is not the same anymore. We try to deal with the people that comes from another culture. This culture is not as loyal as probably we were in the past to a concrete job position. The new people is more thinking in temporary jobs, different changes. So we are in a workforce transformation that means to to try to move our knowledge from a specific user-based way to a more company and information system way. And obviously we are also involved in a set of threats. COVID-19 is the first one, of course. And all of us are asking us ourselves when we will be, we will finish the restrictions and the vaccines and so on. In the meanwhile, we have adopted some kind of remote work that in the past was possible, but was not very usual. But today, there are many tasks that are being done in a remote work, and probably after the COVID, some of these practices are not going to change. Another one, we will recover some face-to-face relationships, but probably we will face a combination. We don't know when the aerospace or the automotive or even the oil and gas industry are going to recover. We are seeing that many companies today, especially in the automotive industry, are producing almost 90% of the capability of there is a trend in the automotive industry to produce and produce more. In other areas, for example, in oil and gas, we are seeing that the problem is the opposite. There is no demand in the market. So everything is uncertain. There is also a lack of skills in the new technologies, for example, in areas like Industry 4.0, artificial intelligence and big data. Probably if you try to look or to follow a LinkedIn, the LinkedIn page, you will find a lot of information, but it's not a practical information. It's very theoretical information. There is a lot of people talking about Industry 4.0, but in real situations, it's not easy to find people that can use these elements in the real life. Also, the Asian exports and especially the pressures over the prices in the steel that in sometimes in the past, in the short past, we saw a lot of problems with these kind of elements, with a lot of stocks in the harbors from Asian steel and so on. And this is always a threat. But there is another, in our opinion, there is another bigger threat, that is the control of some Asian countries. I don't say the name of any country, sorry, but probably you have in the same country we could have. And they are controlling the semiconductor industry and other electronics modules and devices and cards. And this is being a really big threat for the short-term future. So obviously, in all these trends, we can resume or we can summarize that we are living in a VUCA or VUCA environment, where the VUCA means U is volatility, U is uncertainty, C is complexity, and A is ambiguity. This is the environment where we are living, including the iron and steel industry. And we cannot change this environment, but we can live in this environment, and we can try to fix or to adapt our way to think, our way to act, our processes to this area. Believe me, it's easier than it could mean in a first overview, but you need to be willing to change, because the VUCA environment, the common element of the VUCA environment is that you have to be willing to change every time, every day. And in the past, for example, strategic plans take 2 years or 3 years. Today, a strategic plan, 3 years is almost impossible. We are thinking in a strategic about 1 year or even 6 months. So we have 2 possible attitudes. And this is something that we see in our customers every day. There are 2 possible attitudes. The first one is nothing is changing. Everything will be the same after the COVID. Everything will be the same after 2 years, and we will continue producing in the same way are producing today. So in summary, you can sit down to the river and wait for your enemy's dead body. So it's try to see who is able to resist more to the pressures. But the new or another approach is to try to develop a new breakthrough strategy in the company, a new breakthrough strategy that includes the change like a way, like something that is normal. So the normal is not the static situation. We have lived in the last 10, 20, 30 years. The new normal is everything is gonna change, and we have to be experts in adopt these changes. And this is the motivation for this webinar. It was the motivation also for our paper, and is also the motivation for our solutions. In case of improving periodic defect detection, that is something very concrete, and you will be thinking now you have introduced an overall general, but improving periodic defect detection or any kind of defect detection, because the same is a part how we can explain how to move from a static situation to a new situation. So our motivation is, if we can improve periodic defect detection, a very concrete problem, or more generally, if we can improve our defect detection capabilities, we can reduce costs because we can reduce downtime, or we can reduce the amount of low quality products, or we can reduce the energy consumption. It means less emissions in the environment, and labor costs. And we can reduce the reprocessing of scrapped materials. Again, we are reducing the emissions and so on. But also we can increase incomes. We can increase incomes because good quality products without defects allows always better prices in high quality segments. For example, in wire rod, if you try to sell wire rod for the automotive customer, you can sell the same coil in terms of $100 or $150 more by ton. So imagine that you are selling in 100 or 150 means 50% of the price. So you will move from not profitable to profitable company just by producing high quality products. This is the reason because we don't understand, or we didn't understand the reason because only 20% of the companies consider the quality as a way to be profitable, when for us it's something that is clear. And we are seeing in America every day that there are many companies coming from Asia, for example, POSCO in Korea or so, that are selling high quality wire rod. And in the meanwhile, the own American companies or in Mexico and so on are producing low quality steel. We can understand this strategy. Probably it will have a very good explanation. And I kindly request, if you know what is the reason to be focused in producing a standard wire rod instead high quality wire rod for automotive, why not to change the way? Because it's not something that requires big investments. And the most strategy is probably that with the reducing defects and reducing this problem builds a customer loyalty for the future bigger than the current customer loyalty. And in the future, the market is absolutely a customer-centric market. It means that if you don't act thinking and acting for your customer and try to be focused in the standard or in the traditional way of the product, probably you will find that your customer will be less loyal than in the past. And in this case, losing loyalty of customers means to increase a lot in sales or in marketing budgets and so on. So creating long time and fruitful relationships with customers is something that is absolutely clear. How we suggest or how we propose from the technical point of view to base to improve the periodic defect detection and the defect detection in general. There are three main technologies. We could say we have two main technologies and a third area to develop. The first one, eddy current. Eddy current is an electromagnetic technology that is basically, it's physics, but this is not a physics webinar, so I'm not going to try to explain what are electromagnetic fields and these kind of elements, because it could take more time. But if you are interested in understand more about how eddy current works and what are electromagnetic fields and so on, please feel free to contact us, and we can give you an overview, because we have some training courses for introduction to this technology. Eddy current is the primary testing technology in many production lines, especially in hot rolling mills, because it's something that's very reliable. But eddy current tester as primary detection systems has been used since decades in the market. Second one is digital imaging. It's a newer technology that has been used in the last, probably 10 years. And in our opinion is, and we will show why, it's very interesting to complement the eddy current technology, but it's not as interesting as this complement or this integration to be used in a standalone mode. And we will see why. And the third area to develop is the deep learning algorithms. If we have eddy current signals and we have images today, algorithms to make an automatic identification and classification of the defects in real time is, I don't say easy, but it's possible. So eddy current has been used since decades, and probably if you work or you know rolling mill, probably you will know eddy current tester, because it's something that is economically feasible. It's not expensive, and the results are really good. In our experience, about 85%, 90% of the defects can be detected with eddy current. So it's a very good technology, but it's very close to its limits. Today, the limits are in terms of if we can use or not algorithms to take advantage of the huge amount of data that an eddy current system for NDT or for quality control at the end of the line can provide you. Second is digital images processing. And this is something that is very intuitive, that is very interesting, that is being something very common in other industries, but for the iron and steel industry, it's difficult to implement due to the harsh environment. And usually, it's also more expensive, because to take images of wire rod at 100% speed, probably you will need a very sophisticated digital image system. It's not enough anymore to use standard cameras. And also the algorithms present a very high potential for improvement, but they required high-skilled people from one side, and from other side, very good information to train those algorithms. The eddy current technology you can see in a lot of areas. I'm not going to be very detailed in this area, but eddy current is the non-destructive testing technology for the iron and steel industry. in hot production, in cold production, in parts, automotive parts, in tubes and pipes, whatever. Is the let's say is the queen technology, because has been used since decades, and it's always evolving in the same, more or less in the same area. The way it works is whenever there is something that interrupts the electric flow or the electrons flow, it will be detected. This is the main principle. Eddy current has some pros and also has some contras. The pros are it's very reliable, it's very repetitive, it's very resistant to the environment. For the eddy current is not a problem. The steam or the water or the pollution in the air is not a problem. Has been widely used since decades, and it requires a very low maintenance. Sorry. But the contrasts, on the other hand, is difficult to understand. The signal coming from the eddy current testers are not always easy to understand. So skilled people is required, and this skilled people is in electromagnetic fields. That is something that is not very common because it's not in fashion today to be electromagnetic field specialist. There are some defects that are undetectable because the eddy current is good to detect some kind of defects, but there are some specific defects. Some of them are critical. For example, longitudinal overlaps that in many cases are undetectable by eddy current, and it's necessary to use and to dedicate resources, human resources, to the analysis of the results. Digital imaging is another technology today that is evolving very fast because each day there are cameras that are able to take good images at very high speeds. But in this case, this picture is wide rod, 5.5 millimeters, 100 meters by second, 1000 degrees, and you can see the details that are absolutely wonderful. It's like if you could take a picture of the coal or the product in coal, and this is a picture taken in real time. So you can see exactly where it's happening. And in this case, you have different cracks in this section, and then you can, it's absolutely incredible today to have this kind of images to identify the defects. But also they have some pros and some contrast. The pros obviously is very intuitive. If you see here on the right, these pictures, you can see, oh, it's an overlap, very good. Potentially, it can detect 100% of surface defect types because there is no limitation like in the eddy current. And the images can be automatically classified by artificial intelligence algorithms. But the contrasts are that are very sensitive to the environment. In the environment with the steam, with water, with pollution, not all the pictures are good enough to make a classification. Sometimes more maintenance is required for cleaning the optical elements, lighting sources, cameras, glasses, so on. In a standalone mode, requires a lot of training because you have to see many pictures and to say the system what kind of picture you are using, and usually are much more expensive. Our concept and our idea and where we are working is in the integration of the three technologies. The first one is an eddy current testing system, an eddy current tester that takes images. The second one is a digital images system, also very connected. Both elements or both building blocks has to be synchronized on time. That is not easy, believe me. This is a very big challenge. And the third one is by using the images and using the signals, you can implement deep learning algorithms to make a real-time classification of every defect. So The final result is here on the left side, where you can have a map of all the classified defects you can get from this system. So this number of defects or this kind of defects, you can configure the system with your critical defects. And this pattern of maps is very interesting because there is a first utilization of the deep learning or machine learning algorithms to detect a defect and to say this defect, okay, this defect is a hair or this defect is a stamp. But to create this map is directly related with what is happening upstreams with the billet, for example. This map is absolutely or is completely related with the billet where the coil comes from. So there is a second level of artificial intelligence. What are the challenges? The challenge is that I will try to accelerate or to move faster because this is always to repeat more or less the same. But the first challenge is eddy current is difficult to understand. Digital imaging processing is very dependent on the environment, and machine learning algorithms require good quality data sets and skilled people to develop. So this is the challenge, but a challenge that can be overcome. So the best possible solution in our idea is to combine these three elements. This is something that is very interesting. This is the way a periodic defect is detected with eddy current. At the beginning, in the first picture, you can see that probably the level of the threshold of the alarm is set, imagine in the middle of the picture. At the beginning, you can have a signal that is below the threshold. So nothing is detected here. Here in the next coil or in two more coils, the defect is becoming bigger and the peaks are becoming bigger, not exactly, they are still under the threshold. This is the way that the current eddy current system detect periodic defects. So this is the way of current periodic detection. In the next coil, you will see the defect bigger. And say 10 or 12 or 15 coils later, the defect is great. And you can see also the frequency of the defects, and you can take a look of this, and then you can be sure that this is a periodic defect. But what is the problem? From here to here, there are between 15, 20 coils, let's say. It's an example that you don't know what is happening. And the challenge today is to use the information in this area here without the need to go to this this graphics shows the amplitude of the defect during the time. So it's a very simple, graphic. And what we have tried to do until now is using this information to try to perform a frequency analysis in parallel to the standard amplitude analysis. It means that in this case, our frequency analysis can be focused here or here or here or here. So we focus our frequency analysis exactly here, because it means that if we can detect a frequency during the inspection that is compatible with a problem in a broken roll, for example, in this case, if we have these occurrences in the roll, we can identify the roll that is broken by making a matching between the frequency and the roll configuration. And it's not necessary to wait until the defect is becoming big, and it can be done exactly in the first, even the system can make this frequency analysis in every coil. So in every coil, you will have some areas with different frequencies, low frequencies here or high frequencies here that are not interesting for you. for example, these high frequencies, 20 or 52, that is more or less the same frequency of the power network. So it's not, it doesn't give us any information, but this area here gives a lot of information. So it is a complex way to identify periodic defects, but it is possible. And we are identifying periodic defects without images by using just this treatment information and with maths that allows us to change the focus of our processes from the amplitude domain to the frequency domains. And but there is a limit. We only can detect 35, 40% of broken rolls with this frequency analysis. The images give us a picture of every peak. In this case, this is a single images. These images are a very high quality images. So looking at the picture, we can identify what kind of defect we are in front of. And in case of a periodic defect, this is a video that shows how a periodic defect is detected with eddy current, but I will jump over it because it's not, it will take a lot of time, and I'm trying to adapt or to adjust this webinar to the hour. So you can see this video directly in YouTube or in our webpage, just looking the word ISEND or hot discover or whatever, and you can see this video that explains how a periodic defect is detected. And then our idea, and that we are using right now, is in this first stage where we, if you remember, in this first stage, we used it in the past frequency analysis, and still we are still using this analysis. We know that we are now doing with this first frequency or this first occurrence is to look at the pictures that has been generated. In this case, you can see here 2 consecutive images of the first broken or the first broken roll marks that, and if we apply artificial intelligence algorithms here, you can easily identify that this is a periodic defect. And this periodic defect can be detected even if your eddy current tester is in a flat mode without any signal. So this is the reason, because with images, we can complement the power of the eddy current with the power of the images processing. So at the end of the day, what we have is eddy current signals that we can use in the traditional way, that making a frequency analysis, but we also have in this new approach to the solution a set or a sequence of images that are completely related with these peaks, and with eddy current, with machine learning algorithms can be, can be identified in real time. And all of them is working if you are able to show to the customer their results in a useful way. In this case, for example, these are 2 typical screens that are taking care of the user experience. In the first one, we can see the map of the defects in, for example, in a coil. The different colors means different kind of defects. And we can see in the same picture, the pictures belonging to the last occurrence in difference. This is just to have a screen that is continuously showing what is happening. But this is more interesting because you can, for every coil, you can see the results of the overall quality inspection, and all the elements that are in this screen. We have removed the map of defects here, but this is the same here. Quality index is a measure of the quality. And after that, everything is based on artificial intelligence algorithms. So for every coil, we can obtain in real time this map with the classified defects in real time. And this information is and can be connected to what is happening upstreams with the, for example, continuous caster or the billets, or if you have changed something in the rolling mill, or you have introduced a new steel grade or whatever. This map will give you a lot of information about if everything is going okay or not. This is the defect detection processes and the different system in different moment on time, but I don't be stopped here. Again, the user interface is critical, especially because if you want to use artificial intelligence algorithms, you can get accuracy about 95% without any training, because we train our system with pictures and with the different elements that are coming from other systems belonging to other installation. It is useful if you are able to reduce and to summarize the information in the way and that the users can understand. This is a way to summarize information, but this information can be also connected to different elements, or can be shared with even with customers downstreams, or with the steelworks upstream and whatever. And this information is very critical to remove or to avoid the defects since the beginning. We use deep learning and neural networks for our system. We are using these deep learning algorithms based on the state-of-the-art programming languages. We are using Python as the main element. We use data sets to train the algorithms that are based on pictures that we have collected from real installation during the thousands of hours of pictures. So we have very good data sets. We also train the users in a way to train the system with their own data sets. And this is only possible if you are using a very, very sophisticated digital technology. I'm coming to an end, and this is just a picture of one solutions. This is the artificial vision module installed in two strands in a rolling mill. They are working in parallel. These two twin lines can be producing the same diameter or different diameter of different products. This is the vision module, where you can see that the light is very, very impressive, because we need a very, very sophisticated lighting system. The eddy current technology, or the eddy current sensors, are located in somewhere here in the production line. It's not necessary to have the sensors close to the image element, because the integration is done after and using different elements to make that synchronization. This is an example of how is the typical layout in a production line, how it is installed, and all the elements that are part of the solution. You have here the vision system, eddy current tester, different racks for communication, and different racks for the information systems. And in summary, and this is the last minute, in our experience, and in the area we're working now in, is in 3 steps to identify periodic defects that, and believe me, we are today we are very accurate identifying periodic defects. We can identify periodic defects in less than 1 minute, and with a 95% of accuracy. The first step is an eddy current tester will take or will get the signals coming from the electromagnetic fields. The second is we take images of every defect that is informed or that is detected by the eddy current, but not only. We also use the digital images to take images in random areas of the coil to identify other potential defects not detectable or undetectable by eddy current. And the third one is to use algorithms of artificial intelligence for 2 main areas. The first one is an automatic classification of the defects in real time. And the second one is the creation of a map. And then with this map, we can make a relation between these maps and the causes that are the potential reasons for this kind of maps. So this is time to, if you need to write in the question and answer area some questions, we will be happy to answer as much as we can. If there's not enough time to respond to everybody, we will commit, or we will promise we will send you an answer by email. And this is a last picture when you can see a wire rod at 5.5 millimeters speed, sorry, diameter, 110 meters by second speed. This is the nose of the second coil. This is the tail of the previous coil. And that's only to give you an idea of the power of our image system, where you can see that the nose is replacing the steam and the coming from the previous area. So sometimes when you try to cool the wire rod, you are thinking that some cooling elements is uniform, but no, you can see here that the nose replaces the steam and the water. So it's something that for us is very, very impressive, just to give you the idea that how powerful are the images system today. And that's all from my side. Thank you very much. I hope it has been interesting for you. And
thank you, Jose. This is Ken Landau. Sam, there's a couple of questions in there, but Jose, there's just a couple of minutes.
Yep. Jose, there's a couple of questions for you.
Okay.
One of them.
I have aquí I have the first question here is, can you expand a little bit more on how you calibrate the system to recognize the defects in different locations? You need to recalibrate again for the current conditions of that mean. To calibrate the system, we use a data set that has been collected from different rolling mills where we have developed our solutions. We have today, 10, 12 rolling mills. Every rolling mill provides us with different pictures, and these pictures are used to calibrate the system in terms of, almost for every rolling mill, 85–90% of the defects are the same. So to implement the first approach of the system is not necessary to do anything, because we provide our training set. The calibration of the system in terms of lighting or in terms of optics and so on is done once a year, approximately. But the training of the system to identify or to make an automatic identification of the defects is not necessary to do only at the beginning of the installation, because we provide the data sets. And then some of the customers that after our data sets, they use their own data sets. But this is a very similar way, because the data sets allows you to identify almost every defect. So your specific data sets are only for very, very specific defects on very specific areas where we can do research. So at the beginning, the system doesn't need anything to be calibrated, just to install in the system, to start getting information, to start installing the classification modules or algorithms, and to make a first revision. And after that, every year, you have to calibrate your system once a year in terms of, especially the Eddy current tester is has a self-calibration tool, so it's not necessary to do almost anything. But obviously, we have to cover the standards, and the way we do that is we go to the customer once a year and to connect the system and the sensors to a parallel or another external source and to compare the results. But the vision system is not necessary to do anything, just to take measures about lightning and because the lining, in some cases, the lining is decreasing the brightness during the time, but it's not a problem because the system has self-checking tools to do that. So thinking that at the beginning, you don't need anything to calibrate the system because the calibration is done with our own database of defects. And after that, calibration is done once a year, but this is specifically due to the standard calibration requirements coming from external areas. Any other question?
All right, Jose, there's a couple more on there now. We're asking, one of them is what are the defects most difficult to recognize?
Okay, I will answer the question in the other way. The easier to recognize are the defects that are identifiable by eddy current. If the eddy current can detect the defect is very easy to recognize and to classify. The problem is for those defects that are not detectable by eddy current. But the good news in this area is that most of the defects that are not you cannot recognize by eddy current has a very standard pattern. For example, a longitudinal overlap or a longitudinal lap is difficult to detect with eddy current, almost impossible. But with vision is very easy because you only need 2, 3, 4, 100 pictures, and then the pattern is very easy. This is this is the more difficult. Then there is another degree of difficulty for some incrustations, because the incrustations are depending on the rolling mill. So in some cases, for the incrustations, it's not enough with the data set we provide, and we have to take some time to analyze these incrustations. But the good news is that the incrustations is very common, so we can get very good pictures of incrustations. But in our experience, the more difficult to recognize are longitudinal overlaps. And another difficult area is the quality of the nose and the tail, because another area where we have spent a lot of money to research is in the optimization of the nose and the tail area, just to cut exactly the bad areas of the nose, and to try to don't cut too much, just to avoid this one.
So I think there's one last question on there.
Okay.
Have you incorporated this technology in mills producing products other than coils?
Yeah, we are now incorporating this technology in mills producing also flat products, a strip, because in a strip the vision and the images are very simple to take. I mean, it's not simple; it's the same technology, but in a round product, you need 4 cameras, and you need to play with the depth of field to take good images. In a flat product, you only need 2 cameras, and the depth of the field is the same. So it's very simple. We are using the vision technology with a strip. We are starting using also in flat products. And we are using also in some cold production in the welding area of tubes. So there is a lot of areas where we can production. But now our focus today are hot rolling mills, and we are moving now from long products to strip and flat products. And of course, it's possible to use it on billets before charging to the rolling mill. In this case, you don't need the eddy current system. You, in the case of billets, before charging the rolling mill, you just need the picture, the images. You can take images of the billet, and these images are related to also to measure the different dimensions and different elements. With the cameras we use, we can get images, but we can also get information about the dimensions. So In terms of billets, and before charging the billet in the rolling mill, we are not using right now eddy current system because it's very difficult to implement an eddy current coil in a billet with this temperature. And so this is something that, and it doesn't give us too much information useful, but taking images of the billet, that is very interesting because we can save exactly the pattern of the billet. And for artificial intelligence, we can identify the billet without any mark in the billet. We can identify the billet without labels or without other marks because each images of, or each set of image of a billet is unique. So you can identify, for example, exactly the time and the stand and where the billet was produced just with the images. So it's an area very, very interesting to use, but only with vision, not with eddy current. Okay, thank you very much. I hope all the question has been answered, but if you need to ask other questions, please do not hesitate to send us whatever information or whatever question you have directly to the ISTEC. We want to obviously, we appreciate the ISTEC to invite us for this webinar. For us and for an European company, is absolutely challenging to present this webinar in this ISTEC area because we have belonging and we are collaborating with the ISTEC since a lot of years. I joined the ISTEC, I think, in 2014, and I'm very proud to be part of the ISTEC. And we really appreciate the ISTEC to invite us and to give us the opportunity to talk a little bit about how to identify and how to take advantage of this kind of technologies.
Jose, we appreciate you joining us too. That was a very good presentation. Thank you very much. Sam, also, thank you for taking over as the moderator. And we will conclude this. This was done by the Long Products Technology Committee. And our next webinar will be on AI benefits combining process control data with high performance, high temperature, rod surface defects detection technologies for bar and rod mill products. That will be on April 1st. No joke. All right, so that concludes it. Thank you very much for attending, everybody. And I apologize for going over a little bit, but that will be the end of the webinar. Thank you.